Again, thank you everybody for joining us here on this Tuesday evening for our first webinar in the series regarding water management best practices. We're going to be joining together every Tuesday for the rest of this upcoming month and into October, looking at various topics to do with water management best practices focused on dryland strategies. So we're starting tonight with an introduction to the water cycle, as well as agroforestry for water conservation. So Dr. George Powell is an independent consulting agrologist with over 30 years of experience in delivering research and development support for agriculture. He specializes in integrated production systems and blending conservation and production practices. George has his PhD from the University of Alberta in agroforestry, as well as degrees from the University of British Columbia in rangeland ecology and agronomy. So George is based out of the Cariboo and is the right person to be talking about these subjects. So I'm really excited to have him on board. So I will go ahead and stop sharing my screen and let him get started.
Okay, do we have the slide up, Serena?
It's looking great.
Excellent. Good evening, everyone. Welcome to the first of 3 presentations I'll be making focused on building the natural capacity of your farm to trap and hold water. I do apologize. I am having a little technical difficulty here, so I'm not actually able to share my camera view, but that last slide with the picture of me is great because that's me 10 years ago. So looks a lot nicer than I do right now, I think. So the objective on this first presentation is to provide you with an overview of the water cycle and how agriculture is influenced by it and influences the movement of water. So the water cycle. Most of the planet is covered in water, about 70% plus. And as that water is heated by the sun, it is pulled up into the atmosphere through a process of evaporation and transpiration. Transpiration is essentially water that moves through plants first before it enters into the atmosphere. When it gets up into the upper atmosphere, it cools and then returns back to the earth as precipitation. Comes down as rain, comes down as snow, as ice pellets. In a month or 2, you might get all 3 of those at the same time. But that's the major input of precipitation to most areas. And then you also have precipitation that's landed elsewhere that flows overland onto your property. Now, a fraction of that is going to pass through and run off. A fraction is going to infiltrate or soak into the ground and feed our groundwater body. That groundwater is also in motion by the process of diffusion. It moves laterally, some of it moves deeper. When groundwater encounters a topographical change, you get surfacing of water. So, and that's what we refer to commonly as springs. Sometimes you'll get water that's moving deep and it encounters an impermeable barrier, something like a rock layer. And simply the weight of the water forces a column through the center of that water back up to the surface, and those are artesian springs or artesian wells. And of course, we have agriculture, which makes use and pulls water from this cycling. So plants pull some of their needs directly from the soil, but is also supplemented with irrigation. We have water that flows for stock watering and then is excreted back out. And then you have other water uses such as evaporative cooling or processing, washing, that sort of thing that are used on the farm. Key point here is that water is constantly in motion. It's always cycling, and essentially most of it is the same water molecules in motion. There's a little bit of water that is created and destroyed in the process of metabolism, in the process of photosynthesis in plants, but most of that water is just in motion. So with climate change in the interior, we're seeing some significant changes to the water cycle. We're seeing more variability in precipitation when it arrives, and the volumes that arrived are no longer as predictable. Fire and pests such as mountain pine beetle in the upland have caused a lot of mature forests to die or be removed, and this is causing greater inflows into the valley bottoms where most of our farms are located. And it's also some of these changes, drought and fire, have made changes to soil properties which have changed the infiltration rate and the amount that's getting into groundwater. And this also has a big influence, the relative inflows and the changes in infiltration to the amount that's running off. So we're getting, rather than a steady lower level of runoff, we tend to get big pulses of runoff. And of course, with increased heating at the Earth's surface, we're seeing stronger evaporation pressures, so more water lost directly back into the atmosphere, and increased heat stress, which increases the water demands for your crops, for your livestock, and for those other farm uses. So water is integral to sustaining agriculture, but it's really complex and highly variable, the needs at the farm level. These will vary seasonally, so your water needs at the beginning of the year are not necessarily the same as your water needs at peak crop production. They vary regionally, obviously, and by sector. So the water that use and needs from someone who's doing an extensive forage production system is not the same that someone's purely a livestock producer or a market gardener. And they're impacted by both on and off farm factors, this cycling. And these issues and management impacts are governed very strongly by scale. So what you do or experience at the farm level is very strongly influenced by what's going on at the watershed level, which in turn is very strongly influenced by global processes. So the strong effects come down the chain of scalar. In the opposite direction, farm impacts on the watershed are only impactful in aggregate. So you need a lot of farms changing practices to have a change at the watershed level. You need a lot of watersheds changing before there's a global impact. In terms of water management, we have two main streams. The first, which I'll refer to as hard infrastructure. These are built solutions to supplement the system's capacity. So you can pipe, pump, or ditch water to capture additional surface water for your use. You can use tunnels or row covers to slow evaporation from the surface. You can pound wells down into the ground and bring groundwater to the surface. You can enhance your surface storage, so you can create stock ponds or irrigation sources for later use. And you can use dams, ditches, and other means to contain runoff and pull it back into that surface water area. And of course, any equipment used in irrigation, stock watering, or other equipment can be replaced and upgraded in terms of efficiency. These are all hard infrastructure. The main disadvantage, of course, with hard infrastructure is the cost. It's not a free option. What I'm going to discuss over my next two talks are what I refer to as soft infrastructure. So it's changing the soil, it's changing the vegetation complement to build the system's capacity. So we're not trying to supplement the system capacity, we're actually trying to strengthen and build the system capacity to capture and hold that water. And we do that through various means. So with agroforestry and soil organics, we can actually capture more of the precipitation that's hitting the ground. We can increase the infiltration rate and slow the diffusion of that surface water into the crop soil zone. Trees and shrubs have the ability to pull deep water up into shallow soil layers by a process referred to as hydraulic lift. The shading provided by trees and shrubs or the surface cover provided by organics reduce evaporation. And trees and shrubs and surface organics, again, have the ability to enhance the intercept of runoff, so you have less losses out of the system that way. And in addition to building the system capacity, with agroforestry systems, you have the positive benefits of shade to actually reduce your water demand. So it reduces heat stress, that reduces the amount of water required for stock production, for irrigation, for other farm uses. So that was just a brief overview on water management and agriculture. And with that, I'd be happy to entertain any questions. I was really just meant as a prelude to the next two presentations, just to show how they fit in within the water cycle. So if you understand what you're managing, you're better off.
We don't have any questions popping in just yet, George, but I do have one. For the soft infrastructure that you mentioned and seeing those changes, for the region that we're looking at here for the central interior and north central interior, what is the time frame that you would expect to be able to see changes in that soft infrastructure and that increased capacity, like ballpark?
Well, I mean, highly variable because it depends on what you're starting from. So with an agroforestry system, you're not really going to start to see system changes until at least 4 to 5 years after planting. And you won't start to see mature effects in this area until 15 to 20 years after planting. With the soil-based methods, either changing tilth or changing organics, if you're coming from a very poor setting, the changes can be seen almost immediately. And you'll bring yourself up to a new level, a new threshold, and then over time it will build slowly from that. So highly variable, it depends on where you're starting from.
Great, but we are kind of looking for the long game here.
It is a long game. It is something that is a target that you set and work towards. Like many things, you're trying to build your system. Just like your health, your personal health, you do what you can, little baby steps overall that affects the overall health of you in the long term, and little steps, little changes in your management on the farm will make differences to the long term in terms of water management using these practices.
Looks great.
So thank you again, everyone, for your virtual attendance. We're going to shift now into looking at agroforestry as a tool for water management and give you some specifics and some more background on how it actually works to boost your water trapping and water holding capacity, and with some practical examples, I think, for the central interior. I'm going to start with just a really brief introduction to agroforestry, and then I'm going to go through some of the mechanisms for enhancing farm water availability using trees and shrubs with some examples from shelter belts, silvopastures, and riparian buffers. So agroforestry, probably more so than most disciplines, suffers from a lot of technical jargon. And what I've realized in the last few years is that creates a barrier for people when they're trying to learn about these systems. So it's a lot of academic terms that are thrown around, a lot of big words. And so what I'm trying to get people to do is to de-emphasize the jargon, the semantics, and focus on intentions. And focus on your desired outcomes, because that's really what it's there for. It is a management tool. It's a family of land use systems, and we're applying them for a reason. So agroforestry is the intentional planting or retention of trees and shrubs to derive multiple benefits that might be in the form of diversification, various conservation outlets, trying to improve the overall productivity of your farm, or aesthetics or other values, and often a little bit of all of those. From an intentions focused delivery, agroforestry that we would use for cultivated fields would include tree and shrub plantings around the perimeters of fields, and these include things like shelter belts, timber belts, hedgerows, windbreaks, living fences. Agroforestry in the riparian zone, that area in and adjacent to water bodies that is subject to seasonal flooding. And here it's primarily a conservation-driven intent, but it also provides the opportunity for integrating in production or other values. We refer to these as integrated riparian management zones, riparian buffers, or in common parlance sometimes as green zones. And agroforestry used in pastures, where we're blending livestock production, forage production, and tree and shrub production. And this is referred to as silvopasture. In BC, it's probably more commonly referred to as forest grazing. So in using agroforestry for water management, what we're really trying to do is leverage the natural capacity of trees and shrubs to slow down the water cycling through your land. You can't stop a water cycle. You can slow it. The longer that it's on land and buffered and held in place, means there's a longer opportunity for you to make beneficial use for your crop or livestock production. And it often enhances your farm water supply at a lower cost than most engineered solutions. So putting in irrigation infrastructure is very costly. Putting in and maintaining dams and berms and diking is very costly. And they're also subject to failure. There's always a point at which they can be overwhelmed. And another real strong benefit of using agroforestry for water management is that it creates many other co-benefits. Long established for use in reducing the potential for soil erosion. It supports biodiversity. In addition to improving the water quantity, they can improve water quality. And on a climate mitigation theme, they sequester carbon. So about 50% of trees and shrubs are carbon. So as you integrate those onto the farm, you're pulling carbon out of the atmosphere, cycling and holding it in place. So water capture, the soil water that's available in the crop root zone or surface water stored for stock watering and other uses, is really just the difference between your precipitation and other inputs, be that surface flows or subsurface flows, minus the drainage and outflows. Outflows could be in the forms of evaporation, transpiration, or overland flow. And again, just to review that previous slide in the last presentation, agroforestry really can act on many of the elements of the water cycle to enhance the capture and retention of water on your farm. So it can enhance the capture of precipitation. It intercepts runoff. It will increase the amount of water that infiltrates and slowly diffuses into the soil. It can draw deep water up into shallow water layers, can reduce evaporation, and reduce overall water demand by reducing water stress, heat stress on your stock, on your crops, on your buildings. So let's jump into each of these phenomena and give you some examples of agroforestry that you can employ in the central interior to affect them for your own management. Enhancing precipitation capture, snowfall. So shelter belts placed on the leeward side of a dugout create snow drifts that can replenish stockward. So again, a little bit of the terminology here. Windward is the side of the shelter belt on which the wind is approaching, and leeward is the side of the shelter belt that's is protected from the wind. So that zone from the shelter belt out about 20 meters will capture and hold snowfall that's being carried by the wind. So as you slow the wind, it loses energy. Less energy means less ability to carry objects, and that snow just drops out. This is important because 40% or more of the annual precipitation in the central interior BC comes from snow. So there's a large opportunity to hold that water and use it once it melts in the springtime. If you're wanting to distribute snow out onto the field, you would use an evenly spaced shelter belt of shrubs, so a low profile shelter belt or hedgerow, spaced at about 1.8 meters apart. And if you're trying to fill dugouts, then you want to use taller, denser tree and shrub clusters. As with all things in agroforestry, you have to be mindful of your design. So you don't want snow capture where you don't want a water surplus. So I have an example in the region where a producer had a cluster of trees planted next to the sewage lagoon, which was acting to capture the snow that filled the lagoon with snow, and when it melted, it caused the sewage lagoon to overflow. So it's, again, I'll be reminding you throughout the presentation, but it's important to be mindful of your design. We're not just throwing things together happenstance. Agroforestry, trees and shrubs at a watershed level can actually enhance rain capture. So the Earth's surface, when it heats, pushes a column of warm air up into the atmosphere. that warm air actually displaces cooler, moisture-laden air off to the sides. So those rain clouds, if you have a large open area, those rain clouds get pushed out and away from the local area. And so you're losing some of the potential rainfall at that point. With trees and shrubs in place, you're able to cool the surface. You break a little bit of that convection cycle. It's not as prominent. This only occurs at a watershed level. So unless you have a really large farm operation, a big ranch, you're likely not going to be able to affect that change by yourself. But certainly lots of farms within the same region that retain trees and shrubs are going to contribute to less convective loss of rainfall. Trees and shrubs have a very strong impact on intercepting runoff and improving the infiltration of surface water into the soil horizon. So IR, that's the interception infiltration rate, is the fraction of surface water that soaks into the ground. And trees and shrubs work on various levels. So they provide a physical barrier to water movement at the surface. Water moving along encounters surface roots and stems. It slows it or stops it, causes the water to pool, allowing it more time to soak in. Trees and shrubs decompact the soil and create pathways down. So if you have soil that is fairly heavy, it opens up and stops that pooling at the surface and allows the water to move down. And it adds living and decomposing organic matter. So up to 50% of any plant's root system is in root hairs, very tiny, fine hairs. And they turn over quite frequently, usually on an annual basis. And this adds a lot of organics to the soil. And as I'll go into more depth next week with my presentation, organics again act as an agent to wick water down and hold it in the soil profile. And the best example of this in a farm setting is the use of riparian buffers to improve the infiltration rate. So when we look at healthy riparian buffers, they can trap and hold 2, 4, or even more times water than when you don't have a riparian buffer or you have an unhealthy riparian buffer. So just an incredible capacity to trap and hold more water as it's moving through your farm. And that's water that's slowly released for later use for irrigation or stock watering. This graph from the USDA shows the general phenomenon that with large rainfall events, what you will typically see is without a buffer, you get a very large, quick runoff, which can, depending on the volume that's come down, include a little bit of flooding, but that water passes out of the system very quickly. So you get diminished water availability after that peak runoff. With buffers, you see that smoothed out. So that initial input of moisture is put into storage, and then it's slowly released over time. So the same input with both those lines of precipitation, but with buffers, the peak runoff is reduced. And again, it's also important to note that your buffer has to be of appropriate width to the given floodplain. So with a small creek or stream system, a 10, 15, 20 meter buffer would be sufficient because it's going to cover the area of flooding. Something on a large river system like the Nechaco, you might need something in excess of 100 meters for it to function in that way. So it's always scaled relative to the size of the stream or riparian area that you're trying to buffer. And healthy riparian areas create a lot of co-benefits. They really enhance regional biodiversity. They play a very strong role in protecting and repairing water quality. And with moving water systems, with streams and rivers, they really armor the soil and prevent a lot of soil erosion potential. So this is a regional example of a pond that's used for stock watering. And during drought, the water level was receding back to the center. And as that water level receded, the livestock, of course, had to traverse over the bed of the pond to get towards free water. And with that, mud, manure being churned and mixed with that water source, water quality degraded quite quickly. We know there's a very strong relationship between the availability of clean stock water and their feed intake, so this falls right to the bottom line. So better feed intake means better weight gains, so protecting your water quality does have a lot of benefits on many levels. Hydraulic lift. So this is a phenomena that all plants will affect, but it's only really noticeable with large plants, with the trees and shrubs. So transpiration is the process where water in the plant comes from the roots, up the stem, through the leaves, and out into the atmosphere through little holes in the leaves called stomates. And it does that because the plant is opening its stomates to exchange gases for photosynthesis. It's letting oxygen out and carbon dioxide into the plant. And because the inside of the leaf is saturated with water vapor, when it opens those up, that water moves out through the plant into the relatively drier atmosphere. With trees and shrubs, that creates a very strong pull from the canopy through the stem down into the roots. And then ultimately, once it's taken water out of the immediately root zone, it creates a vacuum which will draw water, deep water, up into that shallow profile. And crops benefit from this when they're able to pull or partition some of that deep water that's been pulled up by the vacuum of the trees into their root zone. But you can see that this lift is only a net positive if the tree and shrub roots are not also highly concentrated in the upper soil profile, which I'm defining in the interior regions as being sort of the top foot of the soil. So you can avoid this using two methods. One is to put wide spacing between your tree and shrub rows and your crops. So an alley cropping, shelter belt, hedgerow scenario, or using hydrozoning. And hydrozoning, in essence, is matching your tree and shrub species with your crop species so that they're each concentrating their roots in a different layer of the soil. So some of the regional trees that we would probably want to avoid because in a field scenario, because they do have a lot of low profile or shallow roots, would be your aspen, Douglas maple, some people would refer to that as a vine maple, poplars, red osier dogwood, spruce, and willow. Incidentally, those are the same reasons which actually make them really good candidate species for riparian protection, because they armor that upper soil level horizons and prevent erosion from water. And then also you might find crops that throw more roots deep than shallow have a greater potential for overlap between the tree and shrub component in the crop. So alfalfa, many of your bean varieties, parsnips, many perennial grasses, squashes, and tomatoes have roots down. If the soil is of suitable tilth, they'll have roots down into that 1 foot or below level. Trees and shrubs also reduce water loss by reducing evaporation. So surface water loss is a function of the area that's exposed and the evapotranspiration rate. Evapotranspiration is just the confluence of evaporation, water that goes directly from the soil into the atmosphere, and transpiration, that water that first goes through a plant and then into the atmosphere. And you can calculate evapotranspiration on your farm by using this rather simple equation. Well, maybe not a simple equation. So in plain language, your evapotranspiration rate and water losses are going to increase with warmer air and soil temperatures, with lower humidity, and higher wind speeds. And trees and shrubs alter all of these elements to the benefit of water conservation. So they cool the air in the soil, they increase the relative humidity, and they reduce wind speeds. And an agroforestry application that is commonly deployed for soil moisture conservation in fields would be shelter belts or hedgerows. So shelter belts to reduce these wind speeds primarily, but also to act on the temperature and the humidity. You plant them perpendicular to the prevailing wind in your area. And the protection zone that's created is relative to the height of what's planted there. So the protection zone is 7 to 20 times the height of the shelter belt. So for example, if I've got 50-foot tall tree rows, this is going to create a 350-foot elimination zone. And the elimination zone isn't actually wind to zero, it's wind down to 25 to 50% below what it is out in the open. And then you'll create a 1,000-foot calming zone. And that's wind speeds reduced anywhere from 50 to 80%. Or they are 50 to 80% of what they would be in the open. So 20 to 50% reduction. If I had given another example, if you'd put shrubs in there 5 feet tall, then you would just take 1/10 of that. So a 5-foot row of shrubs would create a 35-foot elimination zone and a 100-foot calming zone. It's very important that shelter belts need to be a little bit of porous, not planted solid. So the goal here is to take some of the energy out of the wind and slow it down, but not stop it completely. And our goal here is to try and achieve about 20 to 40% porosity. You'd measure porosity by looking at it from a side angle, and the air spaces relative to what's covered by stems, branches, and leaves is your porosity. So this graph from the government of Saskatchewan shows that the solid line representing a solid shelter belt initially has a much stronger effect on reducing velocity adjacent to the shelter belt. But then as you move away from that shelter belt, its relative performance is less than shelter belts with various degrees of porosity. The reason for that is that when you have a solid object, it creates a back eddy from the windward side, which negate the sheltering effect at a distance out. And I'll go back up to the previous slide to show you this phenomena. So as wind moves in and encounters a solid object, a portion of it is pushed downwards, where again, it encounters the ground as a solid object and then pushes up. This creates a back eddy. So subsequent airflows are being pushed by that lift that's created there. So they go up and over your shelter belt. So the wind speed isn't diminished at all. So there is a little bit of a complete dead zone when you have a solid, but further out, actually the wind will pick up speed because it hasn't had any of its energy reduced by the trees and shrubs. It's gone over. It's raised itself in elevation. We think of the air as the absence of material, but actually it's because it's composed of particles, it does have a little bit of weight. And so it actually, with that weight moved higher into the air, gravity pushes it to the ground and it creates more energy, more speed. So what you'll often find is it comes down with more energy. It can scour portions of your field out, and you've got no sheltering effect from that point on. So again, very important that your shelter belts should be porous and not planted solid. So trees and shrubs also have a strong effect on light, temperature, and relative humidity. This graph is from research that I did at the University of Alberta. So this is in an aspen forest with either the canopy completely removed, a partial canopy, or a full canopy. And the partial canopy varied from block to block because the goal was to double the amount of light that was reaching the soil surface. But you can see between these three treatments with no canopy, you get an exponential decline in photosynthetically active radiation. So that's the fraction of the sunlight that is actually used by the plants to generate sugars, energy. So it's what it can capture. You also see a decline in temperature and an increase in relative humidity. The temperature and relative humidity phenomena act to conserve moisture, which is a benefit to crop production. Beyond a certain threshold, the reduction in light, however, is a negative. So we're creating a trade-off here between environmental values by the presence of those trees and shrubs. And this trade-off is displayed really well here in this graph that Bird published in Agroforestry Systems. So this is showing pasture production adjacent to a 20-meter tall shelter belt. The solid line indicates the absolute amount of production at a given distance from the shelter belt. The gray line shows the net effect, so it's a cumulative effect over distance. And as you can see, in that first 10-20 meters from that shelter belt, about one tree height out, the net effect is actually yield suppression, very strong yield suppression because of the presence of the trees. But after you get out beyond that, you're getting a net positive. The conservation of the soil moisture overcomes the negative of that short distance of reduction in light. So the gray line there indicating that that net positive can actually extend out 3/4 of a kilometer beyond the shelter belt. And this is what this graph represents sort of average conditions over several years. During a drought, that production boost, because the soil moisture then becomes the most limiting factor to your crop production, can be quite profound, 60, 70, 100% additional production during a drought year. Of course, with shelter belts, you're fixed because the location is placed perpendicular to the wind and it's around the perimeter. With other agroforestry systems, we can compensate by changing the spatial arrangement of the trees. So in a silvopasture with an evenly spaced block of trees, you would have equally displaced light and sheltering effects throughout that silvopasture. But you can arrange those trees into either rows or clusters and arrange the openings so that the sunlight is penetrating up the alleys. And so then you're getting the sheltering effect from the side, from the wind, creating that soil moisture conservation benefit, but not with the entire diminishing of the light availability because of the way we structured those trees. There are also unintended consequences that can occur and you should be aware of from planting tree and shrub belts. That increased humidity may impede crop drying in the late summer or fall. So if you're in an area where you have persistent high moisture problems and you're trying to get a grain crop off or that last cutting of hay dried, it may not be the best option. And of course, trees and shrubs, by virtue of shading out the light, are also reducing the temperature in their understory, and this may delay the soil warming in the spring. So if you have a crop that's sort of critical timing for it to get germinated at a certain point in time, then that may slow the soil warming and the appropriate time for crop production. Shelter belts can be either planted or you can retain them from the native vegetation on the farm. So most of the area in the central interior is naturally forested. So this is an example from horsefly at Big Bear Ranch, Reiner Krumsick's place. And what they did when they cleared the fields here is that they windrowed the trees in coarse woody material across the field. Those windrows resprouted with trees and shrubs, creating semi-natural shelter belts. And this created two benefits. You got no planting costs to establish a shelter belt, and you have reduced land development costs because you didn't have to completely clear, stump, or burn and spread that field to get it into a production state. If you are going to go the planting route, there are some key planning considerations you have to think of up front. First and foremost is planting stock selection. Know your plant hardiness zone, and then match tree and shrub species that are going to be able to survive there. The critical factor in the central interior is winter survival, not typically drought stress survival. So you need something that is frost hardy. With trees and shrubs, the real key is early growth and survival. Once they get established and they are hardy to your zone of production, then they're usually good to go for a long period of time. but they are vulnerable to damage and mortality at that early planting stage. So that might involve putting some extra protections in place from things such as rodent damage or some temporary fencing to keep out deer and other wild ungulates, or your livestock to keep them from browsing or trampling those trees. Remember that it's not a plant and walk away phenomenon. There is a maintenance component to it, so you have to keep a suitable porosity. Early on, when the plants are growing quite vigorously, that means going back in and doing some thinning and pruning potentially to keep the porosity levels appropriate. Later on, you're going to have to go back in and do fill planting with older shelter belts or hedgerows, because over time those plants are going to die and they'll have to be replaced. And at the planting stage, it's always good to think about how those plants and crops may potentially interact. And so you want to avoid crop interference both above ground and below ground. And that's achieved with the spacing and with the species selection. Finally, I just want to look very briefly at not necessarily at trapping and holding water with agroforestry, but actually reducing water demand. The positive effect of shade. So tree canopies shade your crops, your livestock, and your building. This reduces heat stress. It reduces the overall water demand of your farm. It will improve animal welfare, and with improved animal welfare, they're happy to eat and put on weight for you. And with some crop production as well, many cool season plants, a little bit of shading is actually beneficial to their production as well, rather than being in the complete open, independent of soil moisture. And that comes from, again, the phenomenon that these cool season plants are required to open up the stomates, those openings on their leaves, in order to exchange photosynthetic gases, in order to be able to change oxygen for CO2. When it's very hot, very warm, when the leaf temperatures get high, that throughput of water is so great that they have a survival mechanism built into them, and they shut those stomates. But when they shut the stomates, they shut down photosynthesis. So on a very hot, bright summer day, when you might think your crops are growing fitfully, they might be shut down just as a soil moisture or as a plant moisture conservation strategy. So a little bit of shading, reducing some of that photosynthetic input, will keep them going. So just to wrap up, agroforestry practices certainly have the potential to build that natural capacity of farmland to trap and retain water. Trees and shrubs on your farms create many other co-benefits for potential production increases and conservation. The key here is careful planning up front, thinking through the interactions before you get to planting, and that way you can maximize the benefits and avoid unintended consequences. Agroforestry is not just throwing species together in a blender and hoping everything works out. It comes by understanding those natural processes that you're trying to manipulate, and then looking at the properties of individual tree and shrub species and the crops and livestock that are going to be blended with them to come up with the best match.